the next patch we're going to look at, the next thing we're going to talk about is this patch here. And this now is going to be similar to what we did with the plotter, but and the sort of cat art that we made. But we're going to add another layer to this, which is a strategy called dimensionality reduction. And what dimensionality reduction does is it's going to take a data set that has many dimensions, such as 13 MFCC values, and reduce the number of dimensions from 13 down to something that we can plot, for example, 2. And so we're going to reduce the data set from 13 dimensions to 2 dimensions and then plot it in 2-dimensional space. And this idea of dimensionality reduction has a lot of different algorithms that do this sort of thing. There are 3 available in FluCoMa. We're going to look at 2 of them today. We just don't have time to do all 3. The 2 that we're going to look at are called principal component analysis and UMAP, uniform manifold approximation and projection. Before we do that, I'll just say here we're loading in a whole folder of sounds. In this case, I think what I will load in are all of the FluCoMa audio examples. So this whole folder, you can find it in Documents, Max8 Packages, Fluid Core Manipulation, Media is the place where that is. And here I have a whole bunch of, this is the drum loop, the trombone tones, the oboe multiphonics, all of it is all in here. And then we're going to slice it as we've seen before. We'll see our slice points here. A lot of audio, 1,059 different slice points. And we're going to do some analysis. Here we're doing MFCC analysis. There's also fluid spectral shape analysis here. We could try both if we wanted to, or try either, I should say, if we wanted to see how it changes our plot. I'll do the MFCC analysis here, and then we'll print the data set and see that we have, oops, I printed it twice. I think maybe this automatically prints it when it is done. And we'll see that we have 1,058 slices, which makes sense with 1,059 slice points. It has 13 columns, the 13 MFCC values. We can see the identifiers here with our audio analysis values there. And I'll just peek in here quickly to show that this all will look very familiar. We're doing the buff MFCC analysis, doing the buff stats analysis to get the mean value. And then here's this buff flatten object. So when we get the buff MFCC analysis out, what it gives us is for each FFT frame, we get all of the MFCC coefficients. And this is going to be 13 of them is what we're asking for. My slide here shows MFCC 0 is included, but we're actually hopping over MFCC 0 and starting at coefficient 1, because coefficient 0 encodes the overall energy in the spectrum, sort of how loud the sound is. And maybe that's not what we're interested in right now. We're more interested in those timbral relationships. So, so then what buff stats is going to give us is if we analyze this buffer with buff stats, it will give us for each of these coefficients, which are each a time series, it'll give us the statistical summaries of those time series. But with buff flatten, what I want to do is I actually want to take just the mean values of my time series. So I want to use the mean of each MFCC. Here's the mean of MFCC 0, the mean of MFCC 1, etc. And I want to use all of those mean values as my data point. However, in order to add something to a data set, the buffer that gets added to the data set needs to be a single channel. It can be as many frames as you want. That's as many values as you have for the data point, but it needs to be in a single channel. And so what I'm going to do is I'm going to use buff flatten to take these values, the mean of MFCC 0, the mean of MFCC 1, etc., and then sort of flatten them out. So now I have them as one channel, mean of MFCC 0, mean of MFCC 1, MFCC 2, etc. And now I have all the mean values in this flattened buffer, and that buffer I can add to my data set. So that's what's happening here. I'm flattening those values, and then I'm taking the buffer called flat, and I'm using that to add it to the data set. So that's why we use buff flatten. That's the main reason why buff flatten would be used. And buff flatten could flatten it could flatten a whole buffer. Whatever you give it as the input, it'll make a single channel and one big vector of data, which is really for adding to the data set. Okay. So now, the first one we're going to look at is the first dimensionality reduction algorithm we're going to look at is this one called PCA. So PCA stands for Principal Component Analysis. And Principal Component Analysis is going to first analyze the data set that we want to do the dimensionality reduction of. And we do this with a fit call. And we'll look at what it is analyzing in a moment. But first we'll call fit, and then it'll do a transform. We'll call the transform call on the PCA. And it's going to transform that data in such a way that it will be able to show us more of the variance in the data set, more of the differences between the data points. We'll see some visualizations in a moment. It'll sort of rotate the data such that when we look at the data, we can see more clearly how are these points different from each other. And that's what we're interested in here as the first step. How are these points different from each other? Because then those differences and similarities are how we can think about the best way to plot the 13 dimensions in 2 dimensions, but maintain our vision, our understanding of those differences and similarities. Some other things that PCA are really good for are that it helps remove redundancy in our data set. So if we imagine we did some audio analysis and we have MFCC0 included in our data set, and we also have loudness included in our data set, those might be correlated. When MFCC0 is high, the loudness is high. When MFCC0 is low, the loudness is low. And so PCA can actually see that there's some correlation there, and then remove it. Another thing that it does for us is it can help remove noise. And what this means is that if there is some analysis we've done that just isn't useful in showing us the differences between the data points, like it almost seems like the analyses are generated by a random number generator. They just don't seem to explain the relationship between the data points in any way. PCA can actually see that and then find ways of, it can sort of remove that or marginalize that analysis in a way that makes us less focused on that particular analysis. And then, of course, PCA can offer dimensionality reduction, which is sort of the ultimate goal that we're going to be using PCA for here. And we'll see how that works. So if we look at a plot like this, we have some analysis features, could be any type of analysis. And in this case, we'll just think about 2 analysis features for a moment. We've plotted them in 2D space. We can see there's some correlation here. It's interesting to observe some positive correlation. And if we start to think of what if we compared some data points looking just at analysis feature 1, like these 2 points. If we're looking just from this angle, these 2 points are going to look the same, right? They have the same value in this analysis feature 1. And if we were to look at some points in analysis feature 2, we could find points where they would look the same from this angle, from analysis feature 2. And this is sort of one of the problems in the way that these 2 analyses are related to each other, is that we're not able to see in any one dimension, either this one or this one, the full spread of the data to see as much difference between the data points as we possibly can. If we were to think about how to do that, we might say, well, what if I could look at it from this angle? What if there was an axis through this data that was like this? And if I looked at the data from this angle, I actually would be able to see more of the variance in the data. I'd be able to have a better view to see the differences between the data points. And you can see it's not by a lot. If we were looking from this angle, from analysis feature 1, we can still see a pretty good spread of the data. But if we could look from this angle, we could see an even better spread of the data. And so this is what PCA is actually trying to do, is trying to find these new axes that it can draw through our data such that they will give us a better view of the data by which we can see the variance in the data, the spread out of the data points. Once PCA draws this first axis, this will end up being known as principal component 1. It is the axis that will give us the best view of the variance in the data. Then it will find another axis that we'll call principal component 2. That'll give us the second best view of the data. This second view, this second axis, will need to be orthogonal, or 90 degrees, to principal component 1. And that's part of how principal component analysis works, is that all of the axes that it finds need to be orthogonal to each other. I'm sorry, my PowerPoint skills made that not a perfect 90-degree angle, but you can definitely imagine that it is. And then what principal component analysis will do is it gives us these axes as our new axes by which to view the data. So it sort of rotates the data such that we now have our data where the axes are the principal components that it has discovered, that it has identified for us to look at the data from. And we call these principal component 1 and principal component 2. And so we now have transformed the data into PCA space, into a principal component analysis space. We've lost a sense of, one axis being pitch and one axis being loudness and one axis being MFCC1 or anything like that. We've actually lost the ability to look at the data in that way, but we have gained the ability to look at the data and be able to see more of the variance more clearly. Here we gave principal component analysis 2 axes, just analysis feature 1, analysis feature 2, and it gave us 2 principal components, principal component 1 and principal component 2. If we were to give principal component analysis more data, like 13 dimensions perhaps, 13 MFCC analyses, it is going to transform. Let me also clarify for us here that this is not a buffer anymore. I'm looking at a data set. I'm sorry that I'm using the same visual organization for that. That is confusing. But here I have data points with identifiers that are identifier 0, identifier 1, 2. Oh, look, my numbers are off there. Identifier 0, identifier 1, identifier 2, identifier 3, etc. And then these data points have what are probably mean MFCC values. So mean MFCC0, and mean MFCC1, mean MFCC2, etc. So if we were to give principal component analysis a data set that has a bunch of data points that have 13 dimensions, principal component analysis will take in those 13 dimensions and it will give us 13 new principal components. It'll rotate that data in 13-dimensional space. So we now have 13 principal components that are corresponding to each of the data points that we had. And so this is sometimes it's called a projection. We've taken our initial data points in our 13-dimensional MFCC space, and we've projected it into another dimensional space. Here it's a principal component space, where we're looking at not the audio analyses as our dimensions, but the principal components as our dimensions. And again, this is because it gives us a better view on the data to see the variance within the data points. So one important thing about how principal component does this is that it sorts for us in order the principal components that give us more view of the variance, more explanatory power of the difference between the data points first. So these lower order principal components are going to give a lot of explanation about the variance in the data. And then these higher order principal components are going to get less and less useful in explaining the difference between the data points and explaining the variance between the data points. We also can plot this relationship in what's called a scree plot. And here, what we're basically seeing is how strong is the explanation of the variance of the data points for each principal component. So we can see here principal component 1 has a lot of explanatory power of the variance in the data set. Principal component 2 has a little less, has quite a bit less. Principal component 3 has even less, 4, 5, 6. And as we get higher and higher, the principal components that are those higher order principal components become less and less useful for understanding the variance within the data. So the reason why this is really nice is then what we can do is if we want to perform dimensionality reduction, we take our principal component space with all of our data points in PCA space, and we say, well, if these higher order ones are less useful in understanding the variance in the data, and we want to reduce the number of dimensions that we have in this data set in order to plot it in lower dimensional space, let's just chop off some of these higher dimensions and keep the lower order dimensions that do have the most explanatory power. And so that is the way that we perform dimensionality reduction with principal component analysis. And so when we do our plotting in this patch, this is exactly what we're doing. We're having PCA do principal component analysis on 13-dimensional space, but then only keeping the first two principal components and plotting that as an X and Y positions. If I run that button, I think I did the analysis. So here what we're seeing is all of these data points with principal component 1 as the x-axis and principal component 2 as the y-axis. And now if I move around in this space, we can see that we don't have a sense of X and Y being sort of musical features or sonic analysis dimensions, but we can see that sounds that are near to each other sonically are near to each other in this two-dimensional space, and sounds that are different from each other are further apart from each other in this two-dimensional space. And so this is the goal of dimensionality reduction. PCA could be used to help reduce to remove the redundancy and or remove the noise in the data set. And so you might just want to use PCA to not shrink down to 2 dimensions, but maybe shrink down to half the number of dimensions, and hope that by removing those higher order principal components, you are removing the redundancy and the noise. And there's a strategy for doing that when looking at a scree plot. Sometimes it's described as looking for the elbow. So you sort of look for, like, at what point does it really just flatten out and everything seems equally poor, at equally not that useful. So you might say, like, well, by the time we get to 4, we're sort of like on this plateau of just all of these are equally not that useful. And so I might just keep the ones that are more useful. You look for the elbow, you look for the spot where that happens, and you keep the lower order principal components to do some dimensionality reduction as a strategy to remove redundancy and noise. So UMAP stands for Uniform Manifold Approximation and Projection, which we can abbreviate as UMAP. We're not going to talk in as much detail about what this does. We're just going to talk about it more metaphorically because it gets quite mathy quite quickly. But I think some intuition about the process can be very helpful in thinking about how it's used and about interpreting the results that it is giving you. So that's the goal here. Some intuition to give us that ability. Here's how it works. First, in the high dimensional space, so the 13-dimensional space, it creates a tree-like structure connecting points using lines, or connecting nodes using edges. If you're a mathematician or a computer scientist thinking about graph theory, this is creating a graph. It creates a tree-like structure of neighbor relations between the points. So which points are close, which points are far, and it connects the points that are close to each other in order to represent them as neighbors. Then it takes that tree-like structure that it has created and actually kind of tosses it into the lower dimensional space, into two-dimensional space. And at first it tosses it into that space totally randomly. So the neighbor relations are all sort of wrong. You know, the points are sort of randomly spread out in that space. But then what it does is it iterates on the positions of these points, all of them, shifting them around little by little in the lower dimensional space, in our case in the two-dimensional space, until the tree relationships of neighborhoods are more similar to how they were in the higher dimensional space. And this is an iterative process, meaning that just like how we train the neural network, it does some shifts, it checks how good this tree is compared to the high dimensional space tree, and then figures out how it could improve and does a little bit of shifting, and then checks, figures out how it could improve and does a little bit of shifting, checks, shift, check, shift, and it does this iterative process many times until the tree relationships of neighbors in the lower dimensional space is as similar as possible, or I shouldn't say as similar as possible, I should say is sufficiently similar to to the tree relationships that were found in the higher dimensional space. Here's a little bit of a visualization. If we just think about 3 dimensions for now, plotting colors in 3 dimensions, RGB values being the three dimensions. First, we find out what neighbors there are. We find some relationships, connect them with edges, figure out what those neighbor relations are. Then we take this understanding and toss it into 2 dimensions. First, it's pretty randomized. You can see it's just sort of all there. And then UMAP will shift these points around iteratively until the neighborhood relations that it found in the higher dimensional space are going to be more nicely reflected here. And we have these relations present and in our 2-dimensional space. So now if I press the UMAP button, I should say, it will do that process. I'm again calling fit transform from the analysis data set into the reduction data set. You'll notice I'm using the same data set here, calling it reduction, whether it's PCA or UMAP. That's just for ease of data flow in the rest of the patch. And we can see what happens. This takes a little bit longer to compute, and then we get something that looks like this. Okay. There are 2 parameters of UMAP that are worth poking at. Those are num neighbors and min dist. I'm actually going to talk about num neighbors first. Num neighbors refers to the number of neighbors in the higher dimensional space that UMAP tries to find in order to figure out, which neighbors should I try to maintain in the lower dimensional space. And so if we increase this number quite a lot, first of all, the computation will take longer. So that's one thing to be aware of, because it has to do more sort of neighbor checking. We'll get some different types of shapes. And when it creates these data points in 2-dimensional space, it is actually trying to maintain neighbor relations between more points. So for each point, it's trying to keep its 50 nearest neighbors near to it as it does its iterative improvements. If we put it back to 15, when it does the iterative improvements, it is going to try to keep track of 15 neighbors that should end up near a point in the lower dimensional space. The other parameter here, min dist, the designers of the algorithm UMAP describe it as sort of an aesthetic parameter. And what it really controls is, in this lower dimensional space, what is a minimum distance that these points are allowed to be to each other? And so if I increase this to something quite large, like 0.7, and then run the algorithm, you'll notice that these points are going to be generally more spread out in space. And so it's a way to sort of push the points further away from each other to get a different lower dimensional space that you might want for some reason. This might be a more useful performative space. If you're going to navigate this with a controller or something, you might want to have those dots spread out a little bit more in space so that as you move through the space, you have more sounds represented across more of the space. So you can access them a little bit more easily. If we go back to point 1 and do this, this might be useful if we're trying to find like clumps or clusters of sounds that belong together, because then what we get things like this really tightly packed set of data points right here. Like, yeah, those all seem to be very related and very different from these others. And here's another cluster down here, right? Here's a cluster over here that seem to be really tightly packed together. And so a lower min dist might be more useful for finding those types of relationships. And so this min dist parameter you can tweak depending on what it is you're trying to get out of your lower dimensional space, how you're trying to use it. It can be useful to adjust that accordingly. One thing you'll notice is that PCA tends to give, first of all, PCA works much more quickly. So that's one thing, because it kind of does, its analysis is faster and its transformation is really fast, and it just gives you an answer, as you'll notice. So if you want to do something in, whereas UMAP takes like a second and a half. If you want to do something that's sort of online in real time, like, you know, with a rolling buffers recording and an analyzing and plotting, and PCA might be more appropriate for that because it'll happen much more instantaneously and you can have access to the data right away. One downside of PCA is that people tend to find it a less satisfying result. It usually has this sort of like middle cluster like this, and then some extremities like this. And that's sort of how the algorithm is designed, how it works. It'll usually end up with some data space that looks like that. Whereas UMAP can be a little bit more, you know, careful about like really teasing out like, wow, that's really different. So it's like way up there now. And so those results might be more interesting and more useful. And then the UMAP parameters are really useful for thinking about that space as well, like how we want to get into that space. The thing about PCA is that it through its analysis, it does find some redundancy and noise and really be able to like avoid the redundancy and avoid the noise, and then show you a plot that hopefully is avoiding that. UMAP, it doesn't do that. It trusts you that you have selected the analyses, selected the data, done the scaling, everything in a way that it is going to take at face value what those differences are, what those distances are that are being computed. And so, whereas PCA sort of part of the analysis, like tries to hone its view of the data for you, UMAP doesn't do that. UMAP just trusts that the data you're showing it is all really important. So that's another difference to consider. If you use PCA as a strategy to remove some redundancy and remove some noise, that actually could be beneficial for your nearest neighbor search, right? Because then your distances are going to be, you're sort of honing the data set and saying, let's get rid of that stuff that maybe I'm less interested in and try to really focus on the important differences between these data points. And PCA helps you do that. So doing PCA before KD tree could be a good strategy for that. And same with UMAP. I mean, yeah. But again, UMAP won't help you find those potential redundancies. UMAP trusts that all of the data you give it is very important to you.